Hello, everyone, and thank you for attending today's webinar, Open Multi-Service Aggregation at the Edge, sponsored by IP Infusion and UfiSpace. Before we begin, I will cover a few housekeeping items. On the left-hand side of your screen is the Q&A. If you have any questions during the webcast, please type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Near the end of today's presentation, please take 1 minute to complete the survey that's open on your screen. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading Senior Principal Analyst Sterling Perry.
Hi, thank you, Barbara. Hello, everybody. Welcome to today's webinar, Open Multi-Service Aggregation at the Edge, sponsored by IP Infusion and UfiSpace. And I will be the moderator for today's webinar and joined by two speakers, Kai Lee. He is the AVP of Technical Sales with UfiSpace, and then welcoming back Shaji Nathan, who is Chief Product Officer from IP Infusion. So the combination of the three of us will take you through the next hour. Here's a look at the flow of the webinar. I'll introduce really with some market trends and just starting to touch on the role of disaggregation. And then I'll move over to my colleague on the webinar, Kai, who will cover the hardware perspective. And then we'll move through to the software side, the network operating system, and Shaji will walk us through that. And we hope to have about 10 minutes or so at the end for questions and answers. So please ask questions electronically throughout as they come to you, and we'll be gathering them up and try to get through as many as we can. So in terms of the overall market drivers, and I want to address the access network from both the mobility side as well as the fixed network side. And I'll start with mobility. And of course, what's driving mobility today is very much around 5G. The data that's on this slide, it's actually a combination of research from our colleagues at Omdia, which does a lot of the forecasting within our group, and also some data from Ericsson's mobility report. But if you look at the subscriptions, and that's the blue bars, Omdia actually counted over 500 million, half a billion subscribers for 5G at the end of 2021, at the end of last year. A lot of that driven by Asia, but certainly globally. And then the expectation, Omdia forecasts over 1 billion 5G subscribers by the end of this year. So massive, massive growth. Forecasted 55% CAGR, compound annual growth rate through 2026, so pretty significant. On the data side, and this is the Ericsson mobility report data, the orange line, measuring in exabytes per month, forecasting data traffic growth, specifically from 5G, growing at a 77% compound annual growth rate. And this is really just a part of it, and really just the beginning. The whole enterprise opportunity is really just starting to play out now, very much around the 5G advanced capabilities that have been sort of defined around release 18 of the 3GPP 5G standard, as well as standalone 5G as being a requirement to unlock a lot of that enterprise opportunity. And standalone 5G is just starting now. So lots of growth already and lots of opportunity in mobility. If we look at the fixed network, that's not standing still by any means either. This data also comes from our colleagues at Omdia, and it looks at mobile broadband, fixed broadband subscriptions as well as average speeds. If you look at the top bars there, the red bars at the top, that's gigabit per second broadband subscription, greater than 1,000 megabits. And that made up about currently makes up about 2% of global broadband subscriptions. It's expected to grow in this forecast to over 17% by 2025. So massive growth in high-speed broadband. Of course, the average speeds are not going to be gigabit. That's the blue line, but you can see that blue line of average download speeds, climbing significantly over the next 5 years as well to over 500 megabits by the end of this forecast period. Fiber is a huge enabler of both of moving to greater speeds. That's really the main technology enabler that lets operators move to gigabit speeds and even below. But it's also interestingly enabler for higher average revenue per user or ARPUs. Research is showing that fiber deployments actually lead to an increase in ARPU, which of course is a very big deal. A lot of opportunity coming from, or as we move into the post-pandemic world, trends of work from home. I'm obviously working from home myself. This stuff is all expected to continue. One interesting thing that we're seeing is a shift in the consumer focus away from a sharp focus on pricing and really moving towards greater speeds, but also greater reliability is becoming a very important metric. All, really as we move into the post-COVID era of broadband, and our research is already starting to show this renewed or increased focus on the reliability side. So that's kind of a zoom in of the trend. If we zoom out a bit, it really gives us a clear and full picture of the situation that network operators face. We talk about, gigabit and ultra high speed broadband. We talk about 5G, but those are a mix of, within the mix of services that network operators have. They have a lot of legacy services. Of course, they have a lot of legacy networks. In mobility terms, legacy generations of mobility. If you add those all up, the overall services revenue growth picture is not that strong. Omdia forecast, which is shown here, predicts about a 1%, or if you look through this historical period through 2024, it's about a little over 1% compound annual growth rate in revenue. That becomes important because the revenue really is what the operators peg their CapEx total spend and CapEx growth to. And so when overall revenue growth is slow, they have to take that very constrained amount of CapEx and growth in CapEx and put it in the right places in the network, invest in the right opportunities, and of course, fight, really align that with the opportunities and also focus on lowering total cost of ownership, lowering CapEx and OpEx as they deploy capital. And so the network requirements become scaling, of course, to meet the bit demand, but also really pursuing those revenue growth opportunities in 5G and fixed broadband, as I just talked about, and also really focusing on keeping the costs down. Moving into the topic of today's webinar, and I'm just going to highlight it here, and my colleagues will provide the additional detail. But so where does disaggregation fit in, given the big picture that I just talked about? This is a heavy reading survey we did, published in 2021. And we asked here, what are the top factors motivating operators to adopt disaggregation? And the results were really interesting because the initial focus on disaggregation, if we go back 10 years plus, was really on cost. What we're seeing here is a broader focus. And if you look at the top bars in terms of the priorities that the chart is showing, cost isn't really even the primary one. It's in the mix, of course, but faster innovation and flexibility in adopting technologies and launching new services and increasing revenue are the top drivers. And then CapEx is important, as well as decreasing vendor lock-in and really increasing the vendor diversity in the networks are all in the mix. If we kind of map those to the different opportunities and challenges that I just talked through, it's clear that operators are viewing disaggregation as a means to address both the opportunities and the challenges. And if we had to weight it, it looks like they're really pursuing the opportunities to a greater degree than the cost challenge. But clearly, they're all in the mix. I haven't defined disaggregation here. Kai, who I'm going to bring in now, is going to talk more on the definitions and then really get into the role of disaggregation as it relates to the access and aggregation networks that we're going to talk through. Kai, I will bring you in right now to continue, and I'll move to your first slide here.
Great, thank you. And good morning, everyone. This is Kylie with UfiSpace, located here in San Jose, California. Want to reiterate, from some of the driving force of the aggregation, the adaptation to the new technology is certainly one of the things that continue to drive this motivation. So what we are seeing here, and also what we are working with our customer, is the architecture from the traditional vendor, what we call the vendor lock system, which traditionally you will go to a vendor, they will provide you three things, the hardware, the software, and also the service contract and maintenance. And those things are tightly locked. And then one of the things that prevent the end user like yourself is if you want to add a new feature or some of those things, it goes through a pretty interesting process. And by decoupling of those in a disaggregating environment, and basically the time to market with the new feature increase in the software or hardware, we can make it happen a lot faster. So this is one of the things that kind of match with the survey that you saw in the previous slide. So with that, I'd like to kind of show the audience with a reference architecture on a typical service provider environment from the left to the right. And basically, you have the user equipment like your cell phone or 5G devices, typically connecting to a cell tower, versus at home, if you have a residential broadband or some of these newer, what they call the 5G home, the fixed wireless that you can use today in some of the carrier. And from that ties into the radio unit and also the baseband unit. Eventually, that goes into like a cell site gateway, going through the metro Ethernet into an aggregation, and before they hit the central office. So this is kind of a fairly typical design of the telco reference architecture. And what we are focusing today with our software partner from IPI, is to discuss the architecture of how we can decouple some of this functionality. And again, going back, from what the survey actually confirmed is more than half of the end users are looking at doing so that they can innovate time to market and new feature requests much quicker than the usual tradition. And we're going to be focusing on the multi-service aggregation with respect to the aggregation on the central one. And usually, if you kind of go back to like Network Design 101, whenever we add another layer between the central office and the edge, like the cell tower, in this case with the aggregation, the whole idea is really trying to increase the scalability. Think about this. We probably have tens and thousands of residential and cell tower coming into maybe a couple hundred central offices. So having an aggregation layer in between, and basically that will add another layer of scalability so we can home all these devices into the smaller number of central offices in a very timely arrangement. So this is the piece that we're going to focusing on, along with some of the software feature set from our software partner with IPI. So using the previous slide with the reference architecture, allow me to start with this kind of like a traditional network using some of the OEM chassis base that tightly locked between the hardware and software. They are bundled together. You're kind of looking at this as the axis, aggregation, edge, and core. It's kind of what we call the place of the network. And, sometimes you hear the term loosely as the front hall, the mid hall, and the back hall kind of mapped into this architecture. The design is actually okay, except the individual components on each pieces of this network are tightly coupled, from the software and the hardware feature set. So that doesn't leave the end user with too much flexibility, but rather than they are being driven by the vendor who provides you this hardware and software solution. So with the disaggregation, what the picture kind of looks like this. We still follow the same places of the network, the axis, aggregation, edge, and core on the bottom. That whole idea of the architecture stay the same, But the component of each one of those domains, we aggregate them, we disaggregate them by decoupling from the hardware and software. And then that kind of let the end user to do two things. Now they can pick and choose some of the open standard hardware platform, and then using the specific software vendor of their choice to port onto the top of the open hardware. And one thing I do want to kind of emphasize why this is becoming increasingly important is because software nowadays have become a lot more software defined as part of the SDN trend and the SDN architecture. So with a lot of these software defined approach on the software, having an open hardware platform using standard merchant silicon solution rather than a closed-end ASIC from a specific vendor, that gives the software provider tremendous amount of flexibility to port their software with the specific feature set that the carrier that they might need in terms of what feature set they need, and continue to maximize the software-defined network capability, which the trend has been going on for a long time. So this is kind of how we do this together. So from the left to the right, this is kind of the business model. We decouple our white box hardware based on, we call it white boxes because it's based on generic merchant silicon. And we couldn't do this thing like 5 or 10 years ago, and we can do it today. And it has a lot to do because the merchant silicon has really catch up, and their performance are basically catching up with some of the ASIC, the application-specific IC, from a few years ago. So the performance, the throughput and the feature set, they are really catching up with the traditional ASIC. So by decoupling the standard platform on the generic merchant silicon hardware and the software, so in the middle, what we are showing is kind of the model, having the merchant silicon being the foundation, and then we have the open network software, such as our partner from IP Infusion, they can port on top. And then we have all the different modules, and usually nowadays with the SDN approach, a lot of these network operating system architecture is what we call the modular design, and you plug in the different module on top of it. So in this case, we are showing like the routing modules or the provider edge module. So, if I might give an example, if you are routing both OSPF and BGP together on the same hardware platform, you need to fix a bug on OSPF. You actually can bring down the module, patch the bug, but without bringing down the entire kernel. So your BGP is still functioning while you are trying to fix the OSPF module. So this is one of the benefits by, taking this approach. And last but not the least, on the top is the SDN controller or the orchestrator. And with the size of a typical telco network with thousands or tens of thousands of devices, and using the SDN approach, the operator are no longer configuring these devices one by one, but rather than using an SDN controller approach, or sometimes we are known as the orchestrator. So we set the profile and then we push it down using some of the standard like the RESTful API or some of those other standard interfaces that you define on the controller. You schedule them and you push the configuration specifically to those locations of your network devices, and it makes the ease of provisioning and ease of management. And last but not the least, we are very pleased to partner with a lot of these NOS provider, and certainly IP Infusion is one of the tight partners that we are doing this on the model I just explained. And then putting everything together, we talk about the traditional architecture as a reference. Then we plug in the OEM vendor design, which basically we call it hardware and software bundle. And then we go into the same model, but decouple the hardware and software separately, and we talk about the benefit. And now want to bring all the pieces together with all the physical boxes that we are actually building along with IPI. And basically, what we are doing is introduce a couple devices here, and these are all based on the merchant silicon from Broadcom, which happens to be one of the leader on the merchant silicon. And we are using their DNX family. And what we are sharing today that focusing on the aggregation module is their Crewmon 2C. And then on the picture, we show a couple platform as an example, how we build to aggregate like the cell tower, like the home office, like the residential connection, like the ONT or the GPON together, aggregating them into this Q2C platform. We listed a couple different models here, and basically in a nutshell, with the same merchant silicon Q2C, we can build different port density that we can subdivide them into 100 gig focus or 25 gig focus or even 100 gig high density focus by using dual of the Q2C. Keep one thing in mind, most of the telco requirement would like to see what they call the non-blocking solution. So some of these devices in the aggregation layer, we are using a single Q2C chipset, and some we use the dual Q2C because we are providing high density of 100 gig connection, and we want to preserve those as a non-blocking architecture. And all in all, these are the few boxes with the specification. And first of all, Q2C is from a semiconductor manufacturing perspective, this is a 16 nanometer technology as compared to some of the older generation like the QAX and the QMX family. Those are the 28 nanometer. This one is a 16 nanometer. And you would expect this number to continue to go down for some of the newer chip, that we are building the other devices for the central office. But to stay with this one with the 16 nanometer, so why do you care as an operator or as an end user? Because the smaller the nanometer technology, it brings in a lot of benefit. If I can summarize, there are two benefits that actually impact you as the end user to deploy this. One is with the smaller nanometer, in this case the 16 nanometer, the merchant silicon can pack a lot more devices, the different gate transistor into the wafer, resulting into a lot more feature set and a lot more processing power that you can get on the same chip with the same amount of surface area. And the second thing, which is also very important, the smaller the nanometer, the lower the power consumption the chip will require, so we can save costs not only on the power, but the heat dissipation and all that. And with that, what we are showing here are three devices. The Q2C has a 2.4 terabit per second switching fabric, and we try to design all these things stay with the non-blocking or very close to a non-blocking architecture. The middle one with the 64, we label them as the 4.8 because in some cases, with the higher density of the 100 gig requirement by some carrier, we are using a dual chipset design with two Q2C back-to-back. And then last but not the least, on the right-hand side, we are building the same thing but focusing on the 25 gig connection for some of the like the GPON or some of the home residential connection that require 25 gig instead of 100 gig. And last but not the least, there are a couple feature set that we build on top by leveraging the advanced merchant silicon. And the one that I want to call out is the time synchronization. We are focusing a lot on the time synchronization because it's a telco environment with this called the PTP, Precision Timing Protocol, the IEEE 1588 version 2. So we partner with the solution from Microchip and Microsemi, and we support such PTP across the entire network, including with the aggregation devices that we build with the Q2C platform. So that kind of wrap up with the summary. So what we did was we went through from a reference architecture all the way into the specific devices down to the merchant silicon level and why the benefit that we pick a certain chipset is relevant to the end user in terms of the processing, in terms of the heat dissipation, and also the power consumption. So with that, I will turn over to my partner from IPI, and then we'll go from there.
Thank you, Kay. Hi, this is Shaji Nathan, and I'm the Chief Product Officer at IP Infusion. IP Infusion has been in business for almost 20 years, bringing in cutting-edge solutions in control, data plane, and management plane software. And we have over 500 plus customers with tens of thousands of deployment in array of network equipment that covers all the way from home gateways all the way to multi-terabit systems. So I would talk about the software perspective of what Kay just outlined and how we plan on actually addressing some of the challenges that stem from that multi-service provider edge. So going back to that reference architecture that Kay outlined in his diagram, one of the things that stand out is you notice that at the access side, the speeds are increasing. Earlier, it used to be a gigabit PON. If you take a broadband service like a passive optical network, now it's scaling up to 10 gigabit with XGS PON, symmetrical PON, and going all the way to 40 gigabits with the next generation of PON technologies. Likewise, we also want to scale the capacity on the cable networks, as well as on the DSL networks, as well as basically on the wireless side, wireless broadband, fixed broadband, as well as basically mobile. So here the radio capacities are increasing with from 4G to 5G transition happening. You see decomposition of the radio network itself. Basically, the baseband is now becoming more packet-oriented, and it is distributed across with the new 5G architecture. So as you see, there is a plethora of things going on at the edge, the access side. So what happens is basically the aggregation side now comes into focus because this travels the boundary between your transport network, your core, and if you just think about your daily habits, right? When you use that application on your phone, chances are you're basically fetching data from the left side of the network to the right side because you're accessing some kind of an application. So essentially what happens is as more and more devices start coming in, the bandwidth needs increase and the complexity here increases because now you have to scale from what used to be gigabit capacity to terabit scale. That is just the speed aspect of it. For a network administrator, this is a unique challenge, right? On the one hand, you basically have this constant bandwidth demands, and plus you have to roll out new services to keep up with the competition. So as new services are coming in, you need a seamless way to interwork with that existing equipment. And 90% of the time, the networks it's not like a one-size-fits-all kind of approach. There are different cost considerations for different geographies in terms of the average revenue per user if you're looking at a cell site, for instance. And if you're looking at broadband, there are other cost equations that come into play. So how do we actually interwork, right, with the existing topology that you already have? Because there is a mix and match of protocols there at that provider edge. You basically, it can be anywhere from carrier Ethernet, various generations of carrier Ethernet, all the way from 2.0 to 3.0. And then looking at the transport side, you basically have a gamut of technologies. Like if you take IP routing, multi-protocol routing there in terms of ISIS, OSPF, BGP. And if you look at MPLS alone, there are multiple signaling parameters, right? You have LDP-based signaling, RSVP-based signaling. Now, lately, segment routing coming into the picture. Then segment routing V6 coming into the picture. And now to scale capacity, you need to bring in new optics. And with that, you're scaling from 10 gigabit to 100 to 400 gigabit and 800 and beyond. Now, the good news is you have a lot of innovation happening on the COT silicon. The switching speeds are increasing. And basically with the new nanometer density coming in, from a cost per bit standpoint, you get a plethora of new network silicon coming into the picture. Likewise, for optics, you basically have different form factors coming in, pluggable ones that can plug right into that provider edge device of yours. So the ZR, new standards like ZR and ZR Plus coming in. Now, with that comes complexity associated with it. So as a network administrator, you start thinking, how do I actually bring all these elements and take advantage of all these innovations, basically? So hardware is one aspect of it. I'll talk about the software aspect. Now that I've laid out basically what a multi-service access and aggregation and transport looks like, let me get on to address what are the things that you really need. So you need an operating system that can actually keep pace with both with the existing technologies that you currently have, so that you can seamlessly introduce as and when you need a network element to scale up in capacity, be it at the access or at the transport side or at the aggregation side. You basically need that operating system to be able to interwork with your existing device. That's on day one operation, to offer the same kind of services with scale and capacity. So there are a few requirements that actually come in. You need to be able to take in multiple kinds of data plane, right? So it could be a fixed pipeline switch, which scales in capacity from terabit scale, right? And it could be a programmable one, or it could be a mix of both programmable as well as a fixed pipeline. By that, what I mean is like fixed function switches, which do things that are actually pre-built into silicon, and you can't actually change it. But then there is the network silicon where you can, some aspects of it are programmable. So when a new protocol comes in, you can fit in a new encapsulation type, for instance. Quality of service, basically adding new bells and whistles to existing services. So in order to do that, you need a data plane that basically is built on hardware abstraction, which means that it presents a consistent interface to the control plane protocols that are operating. The control plane is the guts of the system because this is where your routing happens, interworking happens here. Your MPLS, for instance, right? All the services basically come into play. So routing, switching, L2 routing, L2 switching, MPLS switching, IP routing, and then getting into the newer forms of way of collapsing the network, basically bringing the control plane, taking out all the complexity from the control plane. Like, for instance, decoupling state information from the network. Like current networks, basically, which are signaling heavy, carry a lot of state information. So things like convergence become an issue as you're working on very high capacity devices. So you need that capability there built into that. So the control plane has to be versatile, has to be modular in nature, needs to be able to interwork with your existing network and also take you to that next level of network transition. Then you need a software abstraction on top, because as network administration teams are becoming more capable, basically there might be newer applications that we haven't thought of as a as a software service vendor. We might not have thought of it, but you have a unique need and you have a silicon that is programmable. So you need to be able to have some kind of a container, just like your cell phone model, where you can actually plan to do some things by yourself that is unique for your network. So we have to have some kind of capability here, software abstraction for not just for operating system vendors like us, but also for third-party vendors, independent system vendors who basically want to bring in new things. For instance, if I want to add a microwave element to an existing router, right, or to add an OLT interface, basically based on, because these new pluggable form factors are becoming possible now. So how do I do that? I need some kind of a software abstraction that actually works with this data plane and makes this new service that is plugging into the data plane look as a part of this overall operating system. So you need to have that ability, some kind of container where you can park in third-party applications. Now to cap it all, you need a management plane. That management plane that manages this disparate set of hardware, right? Because you have got vertical disaggregation as well as horizontal disaggregation, where the components, the DSP may come from somebody else. Basically, the operating system comes from a vendor like us. And now, and hardware basically comes from somebody like UfiSpace. So how do I actually bring that in and operationalize this into the network? I need a consistent interface, management interface. And that has to be automation capable, just like you roll in services today in other domains. In the application domain, you need to be able to roll the network services as well. So you need, at the very basic instance, you need a command line interface. You basically need a model-driven architecture. So a netconf, open config, these are models that are there. So these are the three key aspects from a management plane, from a software abstraction, and a hardware abstraction. So these are the things that we bring together at IPI. So what do? We bring this in OCNOS as a open compute network operating system that we bring in for terabit scale switching. So essentially, it supports a wide variety of silicon, be it from Broadcom, Marvell, Intel, any future capable chipsets that are coming in. And it can even run on the standard CPU or a GPU, for instance, to do the acceleration. And it comes with a full suite of routing protocols, all the way from arcane protocols like ISIS, OSPF, BGP, and MPLS, with all the signaling elements like LDP, RSVP signaling, segment routing, basically interworking between segment routing and MPLS routing, and SRv6 capable. So if you have a network silicon that is SRv6 capable, like the Qumran 2C that my colleague just introduced, you'll be able to actually use that same network element and go from today to tomorrow, essentially interwork with, come in on day one, add scale and capacity, and then on day two, basically you can start rolling services as and when you feel comfortable. And over time, you can actually change your transport technology with that same network silicon. And the same operating system can basically work across the board, all the way from access right into the data center. So the beauty here is basically you get the benefits of multi-vendor capabilities in terms of innovation, in terms of silicon, in terms of new breakthroughs in software engineering as well. And on top of that, it allows you to innovate as well, basically customize it as per your needs. Now, network automation is a key aspect of it. Now, we are getting, these networks are basically, you want to think of it like a time series kind of a device, which is constantly giving you lots of packet metadata. From that, you can glean a lot of intelligence, right? But in order to do that, the devices need to be capable of exporting this at a very high rate, because now we are talking about networks that are going from 10 gigabit all the way to 400 gigabit in terms of port speeds, and 800 in the near future. So as you look at it, the packet metadata that comes in has to be streamed, right? The polling mechanism doesn't work. The SNMP doesn't scale. So you need newer ways, that instrumentation where you can actually feed it into a big data kind of data lake, for instance. So you need analytics to be working on top of it, being able to do some kind of predictive analytics, right? Because now you have all this data, you can get a lot of insights from it. So newer paradigms like machine learning, for instance, in order to be able to do that, you need that right infrastructure in place, right at the operating system level, as well as at the network management layer. So basically, you need the OAM layer to be very robust. So streaming telemetry becomes a very important aspect of it. Then correlating between events, right? You have this disparate set of devices that are coming in. So now the troubleshooting gets pretty complicated very quickly. So in order to do that, how can we lessen that impact? What we provide is basically a natural language-based search based logging system, which basically allows you to work just like you work with Google today to get an insight, right? You can actually do the searches on the log, a Splunk-like interface, basically coming into the network itself. And on top of that, you can add any kind of third-party analytics tool on top of this data lake that you already built. And a service integration bus so that you can add in new applications, basically optimization application, for instance, like bandwidth on demand, for instance. Let's say your network is very unique to you, and you have some security element that you want to bring into focus. So you could do so by plugging in on top of this management layer here with the service integration bus. And you have the appropriate domain controller, because as I alluded to in the previous slides, you basically have a confluence of things happening, right? On the radio side, a portion of the baseband is basically now getting attached to this device. So you have radio transport coming in on one side. On the other side, you have this optical transport. So now you have multiple domains now converging into a single platform, like the platform that the Q2C platform that Kay mentioned a little while ago. So in order to do that multi-domain control, you need a domain controller that basically can control that multiple domains converging onto that single platform. And on top of that, you need an analytics layer and a network automation service, right? So service orchestration. So with this multiple domains, as a network administrator, you want your tasks to be much more simpler. So you want to be able to define this at a higher level. So newer paradigms like Tosca basically are coming in. That has to be working seamlessly with existing network management layers, right? With the existing data models that you currently have in your network. So you need a layer of service automation basically that comes in and plugs right into this new network element. So on day one, you can manage that new network element and still get a single pane of glass, right? You already have a device that is already element management system that is already managing your existing network. So you need some way to plug into this new system that is coming in so that you get an insight. So we provide that capability as well. Not just the operating system, but the software to manage this new paradigms. So how does this all come together? So let me give you a practical use case, right? Taking this UfiSpace 9600 router. So what we have done here is, this is an actual deployment use case that we have validated, tested, and it's being rolled out into a network. Essentially, in this case, the service provider basically had a mix of 4G, multiple generations of radios on the tower. So 4G mainly. So on day one, the necessity was to increase the scale and capacity of that network so that it becomes 5G ready. Then over time, what they want to do is to bring in 5G radios basically on that tower. So here, the first order of business is to basically bring in this CPRI radio that is already there. And they want to actually have a mix of distributed units, a BBU sitting right at the edge of the tower, as well as with the new paradigm, where the DU itself is basically sitting somewhere here. So this becomes almost like a mid-haul component. So essentially, you have a front-haul gateway that is capable of taking in both the eCPRI for 5G and CPRI for LTE, that is the existing network. So a mix of timing and synchronization, right? So with 5G, you basically have much more stricter requirements in terms of timing. And for 4G, it has to interoperate with that old-fashioned radio. So essentially, you have this front-haul gateway that gets aggregated here, and that gets plugged into an existing network. And that existing network is today's IP MPLS based. So it's running seamless MPLS. And essentially, they want to actually cut over from RSVP-based signaling today. They want to decongest the network, basically bring a flatter control plane. So on day one, what we provide is RSVP, LDP-based signaling, because they've got multiple sites with different kinds of transport. So we accommodate that on this particular platform. Then the next part of the network iteration is basically the control plane protocols get flattened. So at some point in time, it becomes SRv4 capable. So what we plan on doing is basically just turn off some of the services and reconfigure this device here, basically to do interworking with that LDP, with the P router that is in the network. And then from there, the third part of the network transition is when they want to run SRv6, when they decommission some of the older generation of the radios, they want to go SRv6 end-to-end. So we are ready. So we start from day one, basically adding scale and capacity, and then bringing in the 5G network element, adding in services using EVPN virtualization services, right? So first, it starts out with a standard VPLS, VPWS, L3 VPN. Basically, these are the three constructs here. And then over time, we basically add in the signaling where we make it SRv4 capable, and then SRv6, where you run IPv6 end-to-end. So this is one example of practical considerations that we take into account using our operating system on a third-party hardware, and basically interworking with all the network service components that are there. And so with that, I want to basically reiterate what we bring to the table. Basically features in terms of common software platform that I outlined, hardware abstraction, programmability for you to innovate, and simplify it. Basically, as networks are not one size fits all, there are multiple considerations there. So we support a wide variety of hardware, and the management plane basically becomes very important. So the simplification through network automation, open architecture, it's built on open standards, IETF, IEEE, OIF compliant. And de-risking it, we provide after-sales service and support, which basically you come to expect from an OEM. So bringing new technologies in without having to risk everything in your network. So that actually plays down to that CapEx and OpEx that Sterling mentioned at the beginning of the presentation. So with that, I hand it over to you, Sterling.
All right, excellent. Thanks, Shaji, and thank you, Kai. Great presentation. So we do have about 15 minutes left for Q&A, and we do have some questions in. I'll start going through those, but for the audience, if you have some questions as in addition here, now's the time to ask them. Let me start. I guess I'll start with Kai. A question about the hardware platform, the S9600 that you highlighted in the presentation. Other than what was presented, are there other use cases for that type of hardware platform? Kai, are you able to address that?
Yes. As the title of the webinar today, we call it the multi-service aggregation. So the box is actually, mainly designed for aggregation. Aggregation is a very interesting characteristic layer. Usually looking for very high density, somewhat low cost type of devices so that you can do the scalability that I talked about earlier. That is the one thing. So to answer your question of the use case, the multi-service piece that we talk about today are some of the examples that we show. Not only we are focusing on the homing, the 5G or the 4G LTE, but also some of the residential connection, the BNG, the fiber broadband and all that. And that kind of, make it kind of like a multi-service type of environment. And that goes back to the utilizing the merchant silicon. Another use case to answer the question that you just bring up is, at the picture, we show this is a one single layer design of the aggregation, and usually that was the purpose is to home tens and thousands of residential or cell tower into maybe a couple hundred central offices, kind of environment. But to take it to the next step, we actually can design this with a two-tier using a spine and a leaf with a hub layer or a spine layer of the aggregation devices using the same Q2C technology like 100 gig, and then the leaf using the 25 gig. So now all of a sudden we have a two-tier design of the aggregation, and we can take the scalability to the next level. And the beauty of that approach is a pay-as-you-go model. I can start with a single layer, and then if I scale to a certain point, I can add the spine and the leaf layer, and then I can continue increase my leaf, and then when we get to a certain limit, I can increase the spine as well to make this thing very scalable. And that goes back to the flexibility of the, this whole open disaggregated design is a pay-as-you-go, and then we make it extremely flexible from a topology perspective for the operator to, go from the initial stage all the way into as the business they grow. So those are the 2 or 3 examples I want to highlight.
All right, thank you. There's a question refers to a specific slide. Let me see if I can push it. It says slide 18, which I believe is this one. And the question is, and it's referencing the 9600, although Shaji, you presented, so I guess I'll give you first shot at this one. Why are you distinguishing between the 9600 aggregation routers and a provider edge router, which is also being shown? And I guess the real question here is, how do you distinguish between a provider edge router and the 9600, the aggregation router role?
Yeah.
Go ahead.
Yeah, that's a good question. It's basically, the same device for some carriers, depending upon the scale and capacity, that 9600 could very well be the provider edge router. And in some cases, it could be the P router. If you look at the higher end models that are not yet out on the Qumran 2C platforms, right? basically in terms of capacity, they can actually scale up quite significantly. So it's just a basic terminology, like it's what the tip uses. But as far as a software vendor is concerned, essentially we do not see the distinction. We just see a raw platform in terms of scale and capacity. Just to reiterate what Kay just said, right? This same platform, like I could basically make it into a broadband network gateway, right? Or it could basically become like a microwave aggregation device. For instance, like we've been doing that even on the earlier versions of Qumran. What you could do is basically have a radio management application and then connect a microwave radio to it. So essentially, it looks like an extension of that device. So in terms of provider edge versus aggregation, we don't make a distinction per se from a software vendor standpoint. It's basically just the terminology that actually comes in. But no, there is no distinction actually. I don't make a clear distinction in terms of hardware, because as a pure play software vendor, we can pretty much turn on functions depending upon the underlying hardware's capability.
All right, excellent. Kai, I don't know if you had anything to add on the on the hardware side.
Yes, I do. Maybe it's good you go back to the slide so the audience can follow what I'm about to say. Okay. So basically, the secret sauce is in the software. If I give you a box with a certain merchant silicon, the software is a secret sauce to make it a aggregation versus a provider edge. That kind of make the distinction. But the one thing I really want to call out why we kind of call this thing out separately is this concept called the separation of services. Doing a network design, as one of the things on the bottom, actually it's on the bottom on this slide here, we distinguish the access, the aggregation, and then the transport, which is the provider edge, and the P node. So at the aggregation, we do this thing as the concept of the separation of services is once, you go into the day two after the design, after the installation, you go into the day two support and the operation. This concept by separating these boxes, devices physically, if the budget allow and all that, it just makes the operation folks a lot easier to manage. So I'll give you a very specific example. Provider edge. Usually it's sitting at the edge of the MPLS backbone, if I can use MPLS as an example. So it's doing a route with distribution between MPLS and BGP. And then the aggregation, and the provider edge usually needs a little bit more higher processing with a TCAM table to cache all the BGP route if you do a full table exchange. And you probably have hundreds or even thousands of access control lists that you need to manage at the ACL, at the provider edge. At the aggregation is a little bit easier because my job is to introduce another layer so I can home tens and thousands of cell tower into maybe a couple hundred central offices. So the configuration on the aggregation layer might not be as complex in terms of like access control lists and all these other things. And that's why when we build a provider edge devices, we build in a TCAM hardware along with the control plane. With the data plane. But at the aggregation, the TCAM is actually optional. Certain carrier say, I really don't have that much to cache at the aggregation because I let the provider edge layer to do that. So the TCAM hardware, we make it optional. So that is another perspective. So if I can summarize it, two things. One is the separation of service to make things easier after the day two support, and certainly to reiterate what IPI just said, the secret sauce is in the software. I can make the same box to look like an aggregation versus a provider edge. And so that's kind of the positioning and the color I'd like to add a little bit. So back to you, Sterling.
Right. Yep, thank you. We've got about 5 minutes left, so let me just see if we can get through a couple more here. One of them, I'll comment quickly, and then it will lead into another question that we might want to elaborate on. But somebody was asking about the market share of white box switch router compared to incumbent. I don't have the number in front of me, but it is quite small. This is new architecture, new type of product that's coming into market. The vast majority is still non-white box deployments today. Across the different segments. I think our presenters would agree with that. The question that's in that somewhat relates is what are the benefits of a disaggregated approach versus the incumbent vendors? I mean, a lot of this, we have an incumbent or traditional way of doing things. Disaggregation is new. There has to be a set of benefits if you weigh one versus the other. What are the top ones that customers are identifying when you talk to them? I don't know, Shaji or Kai, who wants to take it, but the question on benefits comparison.
Sure. From a software,
from a hardware piece. Go ahead.
Go ahead.
There'll be both. We'll do Shaji and then Shaji and then Kai. All right, Shaji.
From a software vendor standpoint, what we see is like newer services, right? And then basically the next thing that comes in is how can I actually interwork with my existing services? So service innovation, I would say, is the key benefit because you're getting both the vertical as well as horizontal disaggregation of components, right? And newer capable hardware coming in, which allows you to do a lot more things on that network device than what was possible. To give you an example, right, I can take that that switch and basically plug in something like a Tibit module on an existing switch if the power and cooling considerations allow me, and convert that switch into basically 128 home OLT device. Basically, that wasn't possible before. Now this is possible, right? And that disaggregation actually kind of helps you. Whereas from an OEM, they basically have a fixed line, but OEMs can also pretty much do the same thing. But with disaggregation, you get a whole host of things that you can bring in very quickly and solve a particular problem. So I think that is basically the key thing. And cost is a consideration as more network silicon comes into, COT silicon comes in, the cost over time will fall down, exactly like what we have seen in the data center use case. So I would say service innovation first and followed by cost.
All right, excellent. Kai, you want to add from hardware?
Sure. I think we had 2 minutes left, so I'll try to do this in 1 minute. Basically, the whole idea with this aggregated benefit is we want to provide a common open hardware environment with the advance of the merchant silicon that is available today. As I mentioned, this kind of architecture might not happen 5 or 10 years ago, but the merchant silicon today is powerful enough to do so. And by having this open foundation, this abstract layer, the software vendor can come in and be creating many, many different features on top. This might or might not be a very good example, but I still kind of want to use it. Is every time I think about the public cloud, you can subscribe this from your public cloud provider. You can provision like a virtual firewall, even a virtual switch, on a generic, type of very powerful processor. And those processors are no longer ASIC specific, so it's kind of like going in that trend with the SDN that we talked about earlier today. So having an open foundation, if I can summarize it, having an open foundation and letting our software partner to be as creative as possible, from an SDN type of architecture. And I really think we can take this, pretty far with this open architecture.
All right, and we are coming very close to the top of the hour. I don't know that we have time. Well, maybe very quickly, like a 60-second, and I think it would go to Shaji. In terms of lowering the cost, you did mention benefits there. How does the common software architecture drive down TCO? What are the different costs reduced? And it's going to be, I guess, more of just of a checklist rather than an elaboration because we just got 1 minute. But maybe hit that one, Shaji.
Yeah. So basically, being able to come up with an open configuration model, right? Basically, being able to use a single pane of glass to bring in this new service innovation. So that lowers your OpEx because you have to bring this new service in at a cheaper, better, faster rate, right? So I would say basically that is the primary consideration. Having the same operating system across the board to solve the problem from one edge of the network to the other edge of the network, and being able to bring in diverse set of hardware using, you don't have to learn new things again and again, and essentially work with what you already have. So that lowers your OpEx, basically.
All right, excellent. That we are right at the top of the hour, so we'll close out there. There should be a survey popped up for the audience. If you can just take a moment to fill out the survey, let us know what you thought before you close out. And with that, we are going to close the webinar. Thank you to Shaji and IP Infusion and Kai and UfiSpace for sponsoring. And of course, thank you to the audience for tuning in today. Have a great day, everybody.
Thank you.
Thank you.